This is part 6 in a series of videos in which I'm attempting to repair this PDP11, and as I mentioned in the previous videos, this is part of a CNC control system. I don't have the rest of the hardware, I only have the controller, so it's proving to be a bit of a headache to work on. And as you can see, I've been putting together some more test jigs to try and do some more testing on this. But I have found another fault that I need to get to the bottom of before I can really go any further with this. And basically it's not responding to a lot of the commands from the remote terminal the way it should. So I need to try and dig a bit deeper into it to figure out why that is. So the first thing I want to do is have a look at the board that currently is causing me the most headaches, and that is the decoder board. So I'll get the board taken out, we'll have a look at it, I'll just briefly explain what it is, and we'll go from there. Okay, so this is one of the cards in question. It's one of the custom cards from the manufacturer of the CNC equipment. And what we're looking at here is a relatively simple board. It's just really three 16-bit counters and some control logic. So each of the axes, the X, Y and Z, is controlled through a motor encoder combination, and the motor speed and direction is controlled through the output of the DAC. So a voltage is generated that's used to control direction and speed. The motor's coupled of course to the CNC machine, but also to a rotary encoder, and the output pulses from the encoder are fed into this board, and it keeps track of the count of pulses. Now, because the PDP is not a fast enough processor to count and process each individual pulse from the encoders, because the CNC machine might be running at quite high speed and generating more pulses at a rate that the PDP couldn't keep up with, in which case it would start losing steps, it would lose positional control, and you'd get all sorts of chaos going on, and the CNC machine just wouldn't cut at all, and certainly not accurately. So the way this system works is the encoder count system is a hardware feature, and the counters, when they're enabled, just count up or down depending on the direction of the encoder. The encoders put out three signals. There is an A and B output, and they're double-ended, so it's plus minus output for A, plus minus output for B, and they are typical encoder signals. They're phased 90 degrees out of phase, and the relative phase depends on the direction that the encoder is spinning, and that's how the board determines whether to count it up or down. There's a third signal that comes out, which is the home position for the encoder, not the home position for the CNC machine, but once per revolution of the encoder, the home position for the encoder pulse is generated, and again it's a differential pair signal. So there are 6 signals that come out, differential pair for A, differential pair for B, and a differential pair for the encoder home position. They're all fed into this board. It keeps track, and also we've got this arrangement down here that is used to decode the board. So we've got what really amounts to a comparator, magnitude comparator. That's just used to detect the address depending on the jumpers that are set. And then in theory what should happen is the board should count up or down, and that's what we want to try and test in this video. I don't have the encoders, I don't have any of the hardware other than what's on the bench here. I only have the PDP controller, so I've had to make up a simulator for the motor encoder, home switch, that sort of thing. So we'll look at that in a few minutes. But the other thing that's on this board that I want to check first is the 6 optocouplers we've got down here are for the home position sensors. So the home position sensors, and these are the home position sensors for the CNC machine, not the home position sensors for the encoders. and the home position switches are fed from the 24 volt rail, so they are using these optocouplers. And if you're not familiar with optocouplers, we'll have a quick look at how they work, and I'll just do a quick demonstration as to how an optocoupler works so that the explanation will make more sense. So I'll just clear the bench off, we'll have a quick look at an optocoupler, how they work, and then we'll get back and continue with the testing of this board. Okay, so this is a mock-up of a typical opto isolator. They usually come in small packages like this, and they're very simple. There's nothing really in these other than an LED and a transistor. This is not, of course, optimized, so it won't work quite as well, but the principle is the same. You have two circuits in effect, and these are used where you want a high degree of electrical isolation. So, for example, you might use them in the feedback loop of a switch mode supply, where you need to send signals or a value back to the input side from the DC output side, but you want to maintain electrical isolation. Or you use them in RS-232 converters, really anywhere where you have two circuits that you want to keep electrically isolated. And typically they have isolation of at least several thousand volts, and as I say, they're using all sorts of circuits. But all that's inside these is effectively an LED, which we have here on the left, and on the right this is just a transistor that I've taken the top cap off. So you've got two current loops. One is just to energize the LED in the same way that you would any other sort of LED. Normally there's a current limiting resistor, but all you have to do is make sure you're passing sufficient current through the LED side of the optocoupler to switch on the LED. And on the output side it behaves very like a transistor. You can kind of imagine that the input signal is being applied to the base of the transistor, but in reality the transfer is just through an optical media rather than direct conduction. So as the light intensity on the LED increases, so the current through the transistor increases in proportion, and what you can then do, of course, is use a resistor or something to convert that current into a voltage, which is what I have here. So I just have a dropper resistor, and what we're doing here, of course, is just simulating an optocoupler. So if I now turn the LED on by connecting this wire to the supply, they are still electrically isolated. They're being fed from separate DC power supplies, so there is no direct electrical connection between these two. But if I now turn on the LED, if you watch the multimeter, you can see that we've now got a good healthy signal on the output. If I block the signal by putting something in the gap, you'll see that the multimeter value drops off, and we can control it in whatever way we want. Now, unlike a relay, which you might want to use in some circumstances, but also where you tend to benefit with an optocoupler is not only do you have the isolation, but you can feed back analog values. It's not an all or nothing, so you can feed back a proportional voltage, for example, proportional current, if you want to control something like a switch mode supply. So sometimes they're used just as an isolated switching device, and sometimes they're used to feed back a proportional signal. Either way, you get the benefit of the electrical isolation. Okay, so that's all that's in them, and all we have to do to make these work is make sure that the output has a current path that can be used for something, and that on the input we have a complete current path to make sure that the LED is energized. Okay, so I hope you found that useful, and each of these optocouplers is an LED transistor. And what we should be able to do is apply 24 volts to the resistor that's feeding the LED, which is the 4K7 resistor that you can see to the right of each optocoupler, and then we can monitor the output and make sure it's switching. So I'll get this board fitted back into the PDP, and we'll test it and see if it's actually working. Okay, so what we'll do now is test the optocouplers on the decoder board, and as I said, the three on the right here are the home switch sense optocouplers. So the way I'm going to test these is I have a wire connected, which is this wire, to the input for the Z-axis home switch. So this is going to the D connector on the back of the machine. And in theory, what I should need to do is connect this to the 24 volt rail, which is this wire. And if I connect these together, then it should activate the optocoupler for the Z-axis, and then the output should switch. It's at the moment pulled high with a 5 volt resistor. It's kind of like the demo I showed, and the value should go low when these two wires are connected together. So we'll get a scope probe. Okay, so we'll connect this scope probe to the input resistor. Okay, that's interesting. We're already getting 24 volts and there is nothing connected to this wire. Now let's get the multimeter and see if that's giving us anything. And that is indeed also showing 28 volts. Okay, now there is a diode across this to prevent damage to the opto isolator. So it's possible the diode is short circuit, so I'll just turn the machine off and we'll check those. Okay, so I'm in diode test mode. But that actually looks fine, so we'll just check there's no direct short to the rail. Which there isn't, so there's something strange going on here. We'll try monitoring the 5 volt output anyway and see what happens. So I'll turn the machine back on. Okay, so I've got the two wires here. We'll get the scope probe back in and we'll monitor the output of the optocoupler. So when I join these two together, we've currently got 5 volts showing on the scope. I'll just turn that gain up a little bit so we can see it more clearly. And that should drop when I connect these two wires together. And as we can see, it's not doing anything at all. So we seem to have an issue possibly with this optocoupler. I'll try the other channels and see if they do the same thing. Okay, well I've tried all three channels and I'm getting exactly the same response, and what seems to be happening here is there is no ground return path for the optocoupler inputs. So the negative side of the LED on the optocoupler doesn't seem to be going anywhere. It's possibly grounded through one of the other cards. So what I'm going to do is put all the other cards back in and then retest this and see if we can make any progress. As I said, the wiring on this is a bit strange and some of the connections do go through other cards, so we'll check that and see what's going on. Okay, so I've been following this line around the machine and it goes to pretty much every board. A lot of these are custom interface cards, as I said, and unfortunately the manufacturer of these boards has been incredibly unhelpful. The owner of the machine has contacted them on a number of occasions and they just haven't responded. So we have no schematics for these, we have no wiring diagram for the machine, and if you're familiar with PDPs, you know they can be a bit tricky to work on at the best of times, but we have here 4 or 5 custom boards and the wiring in them seems a bit strange on quite a few. But this particular line, it goes to at least 4 of the cards and it seems to go to the negative end of the LEDs on most of the optocouplers and also on the transistors. You can see which are the output lines controlling 24 volt signals. So we've got 24 volts going into the optocouplers, and we've got the open collector transistors trying to drive signals onto 24 volt lines. But none of these are working because the negative end of the LEDs in all the optocouplers, or at least half the optocouplers, are connected to this common line. So if I try and buzz this out, you'll see that if I connect to this particular point here, which I know is this line we're looking at, and then look at particular optocouplers, what we'll find is that these are connected to the common point, and without this being grounded somewhere, so if we go to the CPU interface, for example, it's connected. Now whether these are connected or not depends, of course, whether or not all the boards are in, because some of these connections go through some of the boards. But it's connected to here, and I've been following this around, and it goes all around the houses in this machine. It goes to at least 4 of the boards and to quite a few of the pins on these interface interconnect cards. But there must be a sink somewhere. It's obviously some sort of control line to do kind of a global control of the optocouplers. But I've been following it around, and there should be a sink to take it to at least a lower voltage. The positive end of the LED, as we've seen, is fed from the 24 volt line through a resistor, so the 4K7 or 3K9, depending on which particular board we're looking at. But the negative end must be at a much lower voltage to get sufficient current to flow through the LEDs, so it's possibly supposed to go through something to ground. But I can't find a sink anywhere. It's certainly not connected to ground, so even with all the cards plugged in, if I do a measure between there and ground, which is the chassis on this machine, there is no connection. But what I have found is if we follow it around, and this is one of the connections here, this is the CPU interface, which is this one, you can hear it's connected, but it's not connected to ground. But it goes to pin 10 on this D connector. Now this D connector goes to the control panel on the CNC machine, and it goes to pin 10. But if I try and connect to the wire on pin 10, which I've got both connected, then I'm not getting anything. But if I push onto the wire quite hard, then it connects. I've got a wire coming out the other side of this. This is, as it turns out, the pause input control for the machine. So it looks like the pause control works by disabling a lot of the optocouplers. So in other words, it just takes the ground away, the ground sink path away from the optocouplers and stops them switching the outputs. But I've got this jumpered to ground, so this is one of the first things I did when I started working on the machine to make sure it wasn't in pause. I connected that particular pin on this D connector to ground, and that jumper, I've checked the jumper's still there. So if I measure this pin, which is this one, it should be connected to ground, and it isn't. If I put the test meter, you want me to see it, I'm putting the test meter on the other end of the wire that's underneath, that's connected to the D connector, and then to the pin on the D connector, nothing happens. But if I wiggle it about fairly aggressively, so I'm pushing quite hard now on the wire that's wrapped around the pin, it makes contact, and if I release it, it stops making contact. So it looks like we've got a problem here with this Y-wrap connection. Now I've never seen a Y-wrap connection that's failed. I've seen some that have been unwound by somebody, but this looks like it's still tightly wound on there, so it seems a bit strange. So I'm going to have a look at it under the microscope and see if I can figure out what's going on. It's clearly not making proper contact with this pin, and that in turn is preventing all these optocouplers from working because they don't have a ground path to allow the input side LED to turn on. So I'll have a look at that under the microscope and get back on camera and see what we can find. Okay, so what I found was a bit unusual. The wire wrap leads were indeed not making contact with the pin on the D connector, and under a microscope it looks like the end of the wire wrap wire had not been stripped before it had been wrapped around. It was making contact. I assume it was just biting through the insulation. It's the way that wire wrap pins are designed. They've got sharp square corners, square pins, and the idea is that digs into the wire wrap wire. But in this case, there's quite a lot of current can flow through these if all the optocouplers are on, and I think at some point it's just stopped making good contact, and then got a bit of corrosion in there because, as I said, I had to push quite hard to make it make contact at all. Then as soon as I released it, it broke contact again. But without that connection, the optocouplers won't work, and these are for things like the home switches, motor drive, motor control, signals in and out, M relays. A lot of the control lines are 24 volt on this machine, so most of that would not have been working. But now I've got this soldered, I've still got the link in I had before for the pause control, but if I now try and measure this, notice it's now connected to ground. I've got the other test lead on ground, and we are now getting a ground return path, which is what we should be getting. So it looks like previously the machine was effectively in permanent pause mode. So what I'm going to do now is start reassembling this, and we'll retest the home switches and see if they're now working. And in theory I can run those manually as I did before, but hopefully this time the output will actually switch. If you recall from earlier in the video when I tested it before, the output of those didn't switch at all. So this will give us a good idea as to whether we've made any progress here. Okay, so we've got the board back in, and we have the hopefully ground connection in place now through the pause return wire. So should find now that the pin 2 of all the optocouplers are connected directly to ground, so I have the other lead of the multimeter connected to ground. So if we test pin 2, we are now indeed connected to ground. So next thing is I'll power up the PDP and we'll rerun the test and see if we're now getting switching of the optocoupler. So I'll just power this back up. I've got these two wires again, so if you recall, if I connect these two together, it should cause this particular optocoupler output to drop. So we're getting 5 volts on the scope. I'll connect these together, and as you can see, the output of the optocoupler now drops whenever these two are connected together. So I'll test the rest of the optocouplers, and this should now also apply to the other optocouplers that are on this same ground return path. There's about 35 in total that all share this common connection, and it seems the way the pause works is to just basically disable half of the optocouplers in the machine so that certain functions don't work. It's quite a safe way of doing it, I suppose. Rather than having a single input that the software could mess up, this is an active way to disable a lot of hardware functions. But I'll go through the rest to make sure that the other optocouplers are now working, and this also applies to the interface card. The CPU interface wasn't working because not only were the optocouplers not working for signal inputs, but the 24 volt control output lines weren't working either, because they also share that same common ground return path. And the same with the panel interface card that has optocouplers on it that do the same thing, and then the explicit optocoupler card also has exactly the same ground return path. Let's grab that card. So this optocoupler control card, this has exactly the same ground return path for about half of these optocouplers and the output transistors, so this wouldn't have been working either. And all that just because one wire wrap terminal was not making good contact. So I'll get the rest of the boards reassembled, and then we can start doing a bit more testing and see if we've got any further towards a working machine. Okay, I've got all the boards refitted to the PDP, and what I need to do now is to try and drive the CNC parts of the control system with signals it can make sense of. Now, the system normally expects to be driving some servo motors that have encoders, rotary encoders attached, but obviously I don't have those, and nor do I have the specification for them, so I need to try and figure out how to feed signals into this that are going to cause it to count up or down. Now, I won't show you the terminal screen in this video. If you do want to see that, then let me know, but what I'll be doing at the terminal is just monitoring what's going on. I've got it hooked up the same way I've had it hooked up in the previous videos, but what I've got now is this board attached. You've seen this board before, but I've modified it again. It's now got a different code, and the idea of this is it will generate some out of phase signals that are similar to what we would expect the rotary encoder to produce. So it's actually a total of 6 signals that come out of the encoders. There's 2 differential pairs for the general motion sensing, so there's an A and a B differential pair, and the phase relationship of that pair depends on the direction that the encoder is turning. So of course normally there'd be 3 channels, X, Y and Z, and at least on this system, and each of those channels is controlled through a drive servo motor that's attached to an encoder, and then the encoder feeds back positional information in the series of phased pulses. There's another channel on the rotary encoder, and that is a once per turn differential pair signal. So in other words, there's a stream of pulses we get, and then once every full revolution of the encoder we get another differential pair signal, which is the home position for the encoder. It's not the home position for the X-axis on the CNC, it's just to say that the encoder has done a full revolution. So I need to generate those signals, and in this case, because it's a CNC machine, it's most likely to try to home the Z-axis when it's first powered up, just to make sure the tool's not going to crash into anything if it tries to translate it in the X or Y direction. At the moment it's not hooked to anything other than the scope, so this board, I've written the code in a fairly simple way. Let's have a quick look at that. This is a PIC again, and there's a bit of initialization at the top of the code, and then there are 2 modes this will run in depending on the position of this jumper. In position 1, the 2 switches will effectively run it in the clockwise or counterclockwise direction, and that's achieved just with a very simple array. So there's an array of 4 values, which is what these are, and these are the 4 values, the lower 6 bits. If we ignore the lower 2 bits, the next 4 bits up are the A and B phase signal values. The top 2 bits are the home position signals that are used once every revolution. And the way the software works is it just works its way up and down through this array depending on which direction it's trying to simulate. So the code just reads the values from that array. There's a bit of housekeeping to check if we're at the full revolution point, and also to deal with the counting up and down through the array depending on which button's pressed. So that's the first mode it runs in. The second mode, incidentally, if you want to see more detail as to exactly how this stuff works, then leave a comment. I'm going through this extremely quickly, I appreciate that, but most people would know how this works anyway, so I'm just skimming through this very quickly. The second mode, when the jumper is in its other position, it reads an analog input going to the board, and the way the CNC system works is there's a DAC, multi-channel DAC on this system, and that produces analog signals that are used to control the direction and speed of the drive motor, and that can be fed into this board through this connection, and what happens then is that value is used to determine which direction to effectively spin the encoder emulator in, and also at what speed to drive it. We'll have a look at the signals on the scope in a minute. And also there's a once per revolution signal given out. I've got no technical data on the encoders, so I've just guessed at all this, phase relationships between the various signals and also how many pulses per revolution, so it probably won't work properly within the system. Depends how smart the system is, whether it counts the number of pulses per revolution, that sort of thing. But without more information on the actual encoders, then this is probably as far as I can go with this. There's also a kind of a global positioning count within the software in the PIC, and that's what this global position count is, and that's used to determine whether or not to activate the home position output. Now this gets slightly more complex because the signals coming out of the DAC in the CNC controller are plus or minus 10 volts, and of course the A to D and the PIC itself only work on 0 to 5 volts. So what I did was using my Jerry Sim system here, a bit like the DaveCAD drawing package, but this is for simulating electronic circuits. I made a small resistor network that sits at the input of the analog channel on the PIC, and what that does is it translates the plus or minus 10 volts, actually it will tolerate plus or minus 12 volts, into a series of all positive voltages. So it's just a very simple level shifter and divider, and if we then translate that into the left adjusted values for the A to D converter on the PIC, we get this range of values. And what I can then do, of course, is just use this to control the direction the simulator generates pulses and also the speed at which it runs. So I'll just give you a quick demonstration of this using the bench supply to control the speed, and then we'll hook it up to the PDP and see what it does. So this is currently powered up in its manual mode, and if I press one of the buttons, if you look at the scope, you'll see it's generating 4 phased signals, and it's only a 4-channel scope of course, so I can't show you the other 2 signals for the home position pulse, but they are very similar. They just occur once every 100 pulses of the standard phased pulses. If I press the other button, you'll see that the same 4 phases are generated, but 90 degrees the other way. So with this button held down, notice that the yellow trace is leading the green, and if I press the other button, notice the green is leading the yellow. That allows me to manually test the counters in the decoder board, which I've done. I did that off camera, I won't bore you with that. What I can do now, of course, is hook this up to the PDP, power it up, and we'll see if it actually comes to life and what it actually does. The PDP won't boot up properly because I've only got the Z-axis hooked up here, but we should see some activity if it's doing anything at all. Okay, so the board is now hooked up. The 3 LEDs on the left just show the least significant 3 bits of the current phase count, and the 2 right-hand LEDs show the direction that the system is trying to drive the motor. So the right-hand LED is clockwise, left-hand LED of the 2 is anti-clockwise, and the 3rd LED from the right is the home position switch. So what we'll do is try and power up the PDP and see if this comes to life. If it's working, then what should happen is we should see some activity on the phase LEDs for a short time, a bit of activity on these LEDs, and then in theory at least, if it can see the home position switch, which I've got hooked up down here, then it should stop, and I've got the analog input from the DAC connected over here. Okay, so we'll try powering it up and see what happens. Okay, well, that looks quite promising. It's doing something. It's not doing quite what it should be doing. It should have driven to the home position and then stopped. So something's still not right with this, but as I said, it could just be that the emulator is not properly matching what the system expects. But at least it is now seeing the home position switch inputs, and it's also able to see the count. On the terminal, what it's doing, it's not properly updating the XYZ display, which I wouldn't expect it to, because I've only got the Z-axis hooked up here, so the other two aren't going through the self-test, and that's probably why it isn't really doing what it's expecting. And also the rest of the hardware is missing, of course, so the system will not properly initialize. Okay, so a bit more investigation, and I think I'm getting a bit closer now to getting through the initial part of the self-test. I realised that during the self-test there was an issue with the way I have this set up. Now, firstly, I found another fault with the decoder board, in that the values from the optocouplers coming from the home switches wasn't being reflected in the register value. So when I was manually reading the registers, it didn't matter what I did with the home switch settings, the inputs, it was always reading 0, even though the optocouplers were toggling. And I found another fault on the decoder board, so I fixed that, and the registers now reflect the status of the home switches. I also realised that I needed to modify the test jig. There's as well as the DAC output to drive the motors, there's a motor enable line on the output of the DAC, and that is presumably so that the machine can load all 3 axes with the correct DAC values, so there's no skew between the different channels, and then it can start all 3 motors at exactly the same time. And that made more sense. It means it can set the motor speeds for all 3 axes to whatever it wants, and then start all the motors at the same time. But because I wasn't monitoring that with a test jig, as soon as it set the DAC value, this started counting, and I think the self-test was seeing that as an error because it saw it as the motor turning when the motor enable line was still low. So I modified it. It now monitors the motor enable line, monitors the DAC value, and then outputs the hopefully correct sequence of pulses for both the A, B and the home channels of the encoder, and then it simulates the home switch. So when the PIC starts up, it effectively has the position of the head in the Z-axis out in space, 500 steps from the absolute 0 value, and I've set it up so that the pseudo home position is 200 steps from the absolute 0 position. So in other words, it should in theory run back 300 steps, hit the home switch, which in this case is simulated with the 3rd LED from the right, and it's fed out to the controller. It should then stop and drive back off, and then it should move on to the next channel, which will fail, of course, because I only have the Z-axis hooked up here. Okay, so I'll go and reinitialize the terminal, and then we'll get this triggered. I'll reset the machine and see what it does. Incidentally, on the scope, the blue channel is set up to monitor the motor enable signal, so we should see that go high if it's actually trying to drive the motor. Okay, so I've set up the values in the battery back RAM. I've got a battery backup voltage applied to this, so it retains data between reboots. I'll now reboot the PIC controller, so it's in its default start position with the motor out in space, and then I'll reboot the PDP and see if it boots up the way it's supposed to. So it should be driving to the home position. It's now hit the home position, and then we saw it drive back off the other way. So it appears to be doing what it's supposed to. It was driving all the way to the home switch, hit the home switch, and then we saw it drive off, and now it's doing some other things. Looks like the program's trying to do something according to the terminal. I'm not showing the terminal on the screen here because there's just not enough space. It would cover up what I'm trying to actually demonstrate. And we saw the motor enable signal go high as well. So I'll repeat that one more time, and again what we should see is the left hand LEDs cycling as it tries to drive towards the home position. After 300 steps, the third LED from the right should come on, which is the home position, and that's fed out to the controller. It then drives off the home switch, and we'll see the two LEDs on the right are indicating the direction that it's travelling. So the one on the right is when it's moving to or away from the switch, and the one on the left is when it's moving towards the switch. I'll just move the camera a bit closer so you can see these better. I'm not quite sure if you can see the LEDs through the camera. I can't really tell through the viewfinder. And then I'll reset and we'll run it again. Okay, so I've reset the start condition for the PIC. I'll now reboot the PDP. It's driving to the home position. And we saw the third LED come on. It changed direction briefly and then it stopped. So it does appear at least that the machine is now doing what we'd expect it to. It's now going through, looking at a terminal, it's going through some other diagnostic testing, and it's coming up with a diagnostic test fail. That's most likely because the other two channels are not connected to anything. But at least it does seem that if we assume this simulator is a motor and encoder, then it does appear that the machine is at least trying to drive them as it should, and it can detect the proper input signals. The machine, the PDP, is responding correctly to the output signals from the emulator, and so I think we're getting a lot closer to this working. Would of course be far easier if we had direct access to the hardware. We could just plug the controller in and do it that way rather than having to develop and spend time with a PIC emulator. But this does, it's quite an interesting project, and it does give us something to kind of exercise the PDP with without having a huge 3-ton machine that could take our head off at any moment. So hopefully finding this interesting. If you want to see more detail about this, more information about the PIC controller and what it's doing, how the code works, then please leave a comment.